Hello, and welcome to Lecture 2, Biomechanics, specifically Biodynamics. In Lecture 1, we talked about biostatics. Now we're going to add some motion to our living systems and take a look at the different types of motion that they can have. So the plan for this lecture is to go through a quick recap of the previous lecture's content, basically an overview of the most important concepts that I would want you to remember, either in relation to solving problems or for a conceptual part of an upcoming quiz or a test. Next, we're going to head straight into biodynamics, but first we have to go through some physics background. So for those of you who are life scientists primarily, this would be very helpful to go through because I'll be going through kinematics equations and projectile motion as a refresher. Afterwards, kinetic versus potential energy and the law of conservation of energy, as well as an overview of Newton's laws of motion, as well as forces. Once you have all of that background, then we can move on to biodynamics and actually applying all of those equations and physics knowledge to solving problems. So there are several different types of problems that we can look at. And it really depends on what kind of living system you're focusing on. So in terms of biodynamics, you can have motion on land, you can have motion in air, like flying, or you can have motion in water, like swimming. So with the three different types of locomotion, you have to consider different types of forces that are acting on your living organism, as well as different physics concepts that have to be brought in for each of these scenarios. Afterwards, we'll go through a few practice problems and then go through a summary of the most important points. So let's start off with the recap. The first thing we're going to talk about is biostatics versus biodynamics. Very important that you know the difference between the two and what kind of equations you would use for each. We're going to go through a quick slide going through conditions for static equilibrium. Afterwards, we're going to take a look at the three examples we focused on last time, which is biophysics of tension and stress in your head and neck, which pretty much applies to tension and stress for all of your muscles on your body. Then we're going to take a look at the biophysics of muscle and the biophysics of bone. So for each of these topics related to muscle and bone, you do have to know some of the biology, and you do have to know how to solve problems. So where do we start with? The first thing we start with is to understand the forces that act on a body and then analyze the body in motion. So we already introduced free body diagrams last time. Now we really want to put those skills to good use and analyze biodynamics. Previously with biostatics, everything was stationary, so our bodies were still. Now we're looking at our bodies in motion and trying to tie in physical explanations as to why we move the way we do. So last time we talked about static equilibrium and how it's very useful for biostatics because everything is just stationary. So the conditions for being stationary would be that you're not moving or shifting left or right, front and back, and that's translational movement. So if there's no translational movement, then that means you're in translational equilibrium, and that means that all of the net forces acting on your body are going to be zero. So that means that all of your forces are balanced and nothing moves. Next, the other type of motion that you can have is rotation, and that's rotational equilibrium if you don't rotate. And if you don't rotate, it means that all of your rotational forces, called torques, are going to be canceling out. So you end up with a net torque of zero. Now, one of the examples we went through was tension and stress from your head. So with this scan on the left, what we want to see is, what we want to do is try and simplify this so that we can do some physics analysis with it. So we know that our heads are supported by our spine, so the C1 over here, which we can just assume is some solid block. And so that can be your spine. Now, your spine is going to exert some sort of force onto your skull. And so at this point here, it's going to exert some sort of force, which we called R for the vertebral stress. Now, the two other things we have to look at is what happens if your head moves. If we want to keep our head still, our head can move in two different ways. It can move forward, backwards, left, and right. And that point that I've drawn is the swivel, or the axis of rotation, or the hinge. So in terms of what we have to look at for other forces, especially rotational forces that are acting on the object, I know that my skull is going to weigh a certain amount. So let's just assume that the center of mass of the skull is somewhere here, towards the left of the red box that we drew. And because of the weight of your skull, it's going to push down. So we have this going down, and we call this the weight of the head. Now, in order for you to keep your head still, there has to be a counterbalance on the other side. If I have a force pushing down that's tilting my head forward, I have to have a force pushing down on the other side to keep my head up. So this means I have a different color. Over here, some sort of extensor muscle pushing down on the other side with some sort of tension. So those are the three main types of forces that were acting on the human head. Of course, there can be more, but to simplify this, these are the three. So what are the few things that we can calculate? Number one, we're able to calculate the tension in the extensor muscle. So you can apply that knowledge to other parts of your body as well. For example, if you're holding something on your arm and trying to see how much tension your muscles in your arm are going through, then you can calculate that too using the same method. The other thing you can calculate is R, so that's the vertebral stress. W is already given to us because we should be able to figure out the mass of our head or just Google it. So the only two items that we could solve for potentially would be R and T. And just remember, for anything that has to do with static equilibrium, analyze all of your net forces in the linear directions, and then analyze all of your torques in the rotational coordinate system. Next, we talked about skeletal muscle composition, and to practice for some of the multiple choice questions that could come up. Here's one. What is the proper order of skeletal muscle composition from large to small? So if you take a look at the diagrams, you can figure out the composition as it gets smaller and smaller and smaller. And you'll note that the largest piece that we started with was a muscle fascicle. Afterwards, it gets broken down and it's made up of a bunch of muscle fibers. And each of those muscle fibers are then made up of a bunch of myofibrils. And those myofibrils also contain a bunch of myofilaments, or just filaments. So the correct answer would be C here. Just write down C as the correct answer. Now, one of the things that you should really understand is what the sarcomere is, which is the basic unit of a muscle cell, or a contractile unit of the muscle cell. And you should also understand what the sliding filament theory is. So I won't go through everything in detail. You can take a look at the previous lecture. But long story short, your sarcomere is the single unit within your muscle fibers and your muscle filaments that helps you contract. So we call that the basic contractile unit of muscle. So there are two myofilaments that make it up. There's actin and there's myosin. The actin is actually shown in, let's see where the mouse is. So the actin is shown here in purple, and then you have your myosin in green. And if you take a look at the green, you have these myosin heads that come up and stick to your actin. And it's these heads that kind of push your actin closer and closer to the M line, which is in the center of your sarcomere. So because this is a contractile unit, the goal is to get the actin and the myosin filaments to cross over each other. The more they cross over, the more contracted your muscle is, and the more relaxed and farther apart they are, the more relaxed your muscle is. So understanding how they form these cross bridges and how they generate that stroke to move the actin closer to the M line would be very important. In terms of the mathematics of muscle contraction, we were presented with quite a few equations in the previous lecture. These are the ones that I think are the most important. There's the rate of contraction, V. If you assume minimum length to be xm of your muscle and assume that the length of your muscle is x with a shortening constant of k, then you can see that the rate of contraction of your muscle is k times the difference in the length of your muscle. So it would essentially be k delta x. Next, you have muscle power, which is presented by P. And power is always some sort of change in energy over time. The only unique thing about muscle power is that your energy doesn't just come from the work that your muscle does, but also the heat that's being generated. So you have to remember that your E, total energy, is equal to delta W, which is your muscle's work, plus delta Q, which is the heat. And each of those are equal to their own equations. So delta Q for heat is equal to A, some sort of empirical constant, times a change in length. And muscle work is delta W equals to mg times delta X. So once you have that, you can figure out an equation for P. And so it's essentially V times mg plus A, a short form of it. And if you have muscle power and the total energy, you should be able to solve for the mass-specific muscle power. So in terms of the mass-specific muscle power, what we're looking at here is how much work does a specific area of the muscle do. So it's a subset of the total amount of work that's being done. So we call the mass-specific muscle work EM because it's a small component. And so your PM for your specific muscle power is going to be that energy divided by T. And so you end up with mv squared over 2mt, where m is the mass of the body and little m is the mass of your muscle. Next, we took a look at how bones acted as jointed cantilevers. So one of the most important things that you will have to know is how to label a free body diagram if we give you a picture of an arm or a leg. So understanding how to find the tension in certain muscles that we point to, that would be important as well. So the take-home message from this is that your bones, especially your long bones like your arm, can be considered beams or cantilevers, and they're attached at the joints or specifically hinges. So you can move the two beams with respect to each other based on the joint that they're connected by. So with the joints as pivot points, we would be able to analyze static equilibrium in many cases, figure out your force diagrams or free body diagrams, and then apply static equilibrium analysis by making sure all the forces and torques balance out. Then you can isolate for a specific term and calculate for tension or stress along the bone. So now we're moving on to the foundations of kinematics. And the foundations of kinematics essentially refers to your kinematics equations, your projectile motion. We're going to take a look at kinetic versus potential energy, as well as the law of conservation of energy. So all of these combined together go through all of the equations and concepts you would have to know to solve for many questions related to motion. So you've probably seen the kinematics equations. The kinematics equations define motion when there is constant acceleration. So it doesn't mean that there's no acceleration, it means that there's constant acceleration. And that means that there is a net force acting on the object. So in terms of displacement, we have d, which represents displacement. Velocity is always going to be the change in displacement over the change in time. And then acceleration is the change in velocity over a change in time. So those are the three equations for that. Specifically for the kinematics equations, there are 5 that you would have to know. 2 of them are quite similar and they're on the right side over here. But we apply these equations for linear motion in the x or y direction separately. So the first one is d equals to 1/2 of v1 plus v2t times t. And you'll notice that there's no acceleration term in there. So if you're trying to solve for a specific quantity, you pick the one that has the variable that you need to solve for. And then if you're missing a couple variables, see if there's another equation that you can use to solve for that and substitute it in. So these are the 5 kinematics equations, and they help us define linear motion in the x or y direction. So one of my favorite examples of going through projectile motion is just Angry Birds. Oops. So there's my Angry Bird and the TNT. Not sure if it's still popular, but I played that quite a bit. That's essentially projectile motion. And if we kind of take this and move it onto the next slide, we can break it down into different components. So by breaking it down, what I mean is that you can, let's see here. You can say that there's a velocity, v. So when the Angry Bird or the object goes up and is shot up into the air, it's going to have an initial of v. So we call that v for now. One of the most important things is breaking it down into its x and y components. So you can have something like that. This means I have a horizontal velocity and I also have a vertical velocity that I have to consider. In terms of the vertical velocity, I can use trigonometric rules. So if the initial velocity is angled theta from the horizontal, then that means I can use sine. Just put this on a separate area. I can use sine of theta, which is equal to opposite over hypotenuse, which is Vy over V. So Vy is equal to V sine theta. I can also have cosine of theta, which is equal to Vx over V. So my Vx is equal to V cos theta. So those are the 2 types of equations that you can use to break down your vector. The next thing I want to mention is that in a lot of cases for projectile motion, you might want to take a look at what happens here at a maximum height. Let's call it H max for maximum height. And then if you drag it down here and draw the ground, so that's the ground. You can figure out the distance traveled. So we can call this delta x, or d, called dh. So the distance traveled to get to h max. You can also take a look at what happens at the very end of this. So when it hits the ground again, it's going to take a total amount of time, and also it's going to the distance traveled will be d max instead. So these are just some basic drawings to show you how to approach projectile motion. But the first thing is really just breaking down your vector into its components. So the first slide I have is breaking down projectile motion like we just did. So just to repeat, I have this being Vx equals to V cos theta, where this is theta. And then I have Vy equals to V sine theta. So I have both of those. So when I take a look at these and I want to try and solve for certain quantities, maybe I'm being asked to solve for V, maybe I'm being asked to solve for acceleration. The first thing you should do is draw a coordinate system. So my coordinate system, the easiest one to choose, would be to make the x direction, horizontal direction, and the y direction positive. So I'm going to consider up as positive and right as positive as well. And in terms of applying the kinematics equations, you'll have to be able to split them up into the x and y direction. So this means I have, let's see, x. So we break it down in the x direction, and we break it down into the y direction. And then we apply the kinematics equations to each coordinate system. So in the x direction, I know that I have Vx equals to V cos theta. The other thing I know about the x direction is that my acceleration is constant and it's 0 because the speed, the horizontal speed, is going to be constant. And so the derivative of a constant is 0, so that means acceleration is 0 in this case. Just write a is equal to 0, or ax is equal to 0 for the x direction, which means there's pretty much only one equation that we can use. You can derive it in many different ways, but I'll just write it down here. Vx is equal to some distance traveled over t. So this is truly the only question that you would really have to use. And in most cases, you would have to solve for Vx, d, or t, specifically t, and then use the value for t and move it to the y direction, because the only things that are shared between the two directions is your time. Okay, so for the y direction, you can use all of your kinematics equations because you have gravity acting on the system. So if up is positive, then gravity is down, and my acceleration is equal to negative g. Oops, let me just move that over. So what are the values that I know? I know a is equal to negative g. Let's try solving for some value at the maximum height. So for the maximum height, we know that it's not just a is equal to negative g. We also know that the velocity at h max is equal to 0. So v2 is equal to 0 meters per second. v1 is equal to vy, which is equal to v sine theta. So I have v1, v2, and I have a. So it seems like the only thing I'm missing is d, which is dh, dy, and t. So there are two ways of approaching this. If I want to solve for if I want to solve for v, if I want to solve for dy or t, I could usually cross these two over the border and be able to figure out the rest of my variables using different kinematics equations. So there is a practice problem for projectile motion later on that you can try out. Next, we have kinetic versus potential energy. And basically the differences are kinetic energy is the energy of motion. Gravitational potential energy is the energy that objects possess due to their position in some sort of field. In this case, a gravitational field. So for kinetic energy, it has to be based off of some sort of variable related to motion, and speed or velocity is the best one to choose. It's also affected by mass. So the heavier the object, the slower it's going to move. So for Ke, you have 1/2 mv squared. For gravitational potential energy, you have Pe equals mgh. And the most important thing is to know that the law of conservation of energy holds. So the total mechanical energy of an isolated system is constant and there can't be change. So what this means is if I'm taking a look at a certain situation, I have an initial state and I have a final state. The initial state has some total amount of energy and the final state also has some total amount of energy. Those two totals are going to have to be equal due to the law of conservation of energy. And each of those totals is called the mechanical energy. So the mechanical energy represented by ME over here in red, that is equal to Ke plus Pe. So it's the combination of kinetic and gravitational potential energy together. Now, if you have a spring in your system, then you'll also have a spring potential energy, and so your ME will encompass all sorts of conserved energies as its total. So if I can say MEI is equal to MEF, I will be able to create the next equation and go from here to here. So I have KEI plus PEI, figure those out at the initial state of the system. Then I have KEF and PEF, figure those out at the final state of the system, and then be able to move on and substitute what I know those equations to be, which is above. So KEI is going to be 1/2 mv1 squared because v1 represents the initial speed, and then PEI will be mgh1, which represents the height initially. So now we can analyze energy in projectile motion, and it makes things a lot easier if we don't have to decompose things into the x and y direction. All we have to analyze is the total energy at the initial and final stages. So knowing the magnitude of velocity is much more important than decomposing it into its horizontal and vertical velocities. So once you have the initial and final velocities and the initial and final heights of your system, then you'll be able to apply the law of conservation of energy and solve for the variable that you're looking for. So let's take a look here. I know that this is the initial stage. So for I know that initially Vi is equal to V. So that's the initial speed. I know that the initial height, because it's on the ground, that has to be 0. And let's write down KEI is equal to 1/2 mv squared, and PEI is equal to 0 because it's got a height of 0. Next, I take a look at my final position, which before we took a look at the peak of your projectile motion. So that's going to be F. And here I know that I'm going to have a certain speed like this. So there's no vertical speed, but there's still horizontal speed. And so that's going to be a magnitude of V2 or Vx. Let me just erase that a bit. So Vx stays the same throughout, so we know that that's Vx. So then we can say that is equal to Vf. Next, you know that the height, hf, is equal to hmax. So therefore, I'll be able to figure out my final kinetic energy, which is 1/2 mvx squared. And I'll be able to figure out an equation for PEF, which is mg hmax. Now that you have your initial and your final kinetic and potential energies, you can use the law of conservation of energy and set MEI equal to MEF. If we're trying to solve for Hmax, then I put everything together. I have 1/2 mv squared equals to 1/2 mvx squared plus mg Hmax. And then I just solve for Hmax. So this is just one example of how to use energy in projectile motion. Of course, in this example, I'm just trying to find Hmax at the peak of the movement, but you can also try and practice yourself by changing the initial and final states. So now let's go through an overview of biodynamics. First, I want to talk about how motion can be described. Afterwards, we're going to talk about Newton's laws of motion, which is absolutely crucial in order to analyze movement, and then a brief overview of impulse and momentum. So how can motion be described? There are various different ways that you can do so. Number one, you can leverage energy for different scenarios like we just did with the last example. All you have to do is apply the law of conservation of energy for your initial and final stages. We also were able to leverage our kinematics equations by breaking down the system into its x and y components. In terms of when you can use kinematics for projectile motion, anything where acceleration is possible due to a net force, whether that is a net force of 0 or not. The third way of looking at motion would be through Newton's laws of motion and forces. And in terms of Newton's laws of motion, there's 3 of them that I'll go through, but there are 2 that are extremely important that will come in handy when you're drawing free body diagrams. So for all of your biodynamics problems, you will be required to draw a free body diagram with all of the forces labeled correctly. And in terms of applying this, it means you'll have to read the question, analyze all of the forces that are acting on the object, figure out what kinds of forces are acting on your object, and that is going to change depending on where your object is and what it's interacting with. Next, you draw a free body diagram, do all the labels, and then just come up with a bunch of equations based on Newton's second and third laws. Once you have a bunch of those equations, you'll be able to see whether you can solve directly or whether you need to do a little bit of algebraic manipulation in order to get your answer. So Newton's laws of motion, there's 3 of them. Newton's first law, what it's saying is an object remains at rest or continues to move at a constant velocity unless it's acted upon by some sort of external force. So any object that's in motion will stay in motion unless something changes. So keep in mind that is essentially what's happening with your horizontal velocity for projectile motion. In the x direction, what's happening is that your object is continuing to move at a certain velocity because there's no additional force that's stopping it in the left or right direction. Now, if there's wind, then that would change the situation. With Newton's second law, it says that the net force of an object is equal to its mass times acceleration, where you have your equation F equals ma. That's going to become very handy. Newton's third law is quite straightforward. For every action, there has to be an equal and opposite reaction. So if I'm pushing something, an object, that object is also pushing back at me in the opposite direction. So that means I have the force of the first body acting on the second body is equal to the force of the second body acting on the first body in the opposite direction, which is where that negative sign comes from. Now, because we're on the topic of forces as well as movement, we have to consider impulse and momentum. So we won't focus on this as much in this course, but it's still something good to know, because whenever you're talking about an object, especially a living system that's in motion, it's going to have momentum. So I want to go through what an impulse is, and then define momentum. So an impulse is exactly what you think it is. It's an intense force that's exerted for a short period of time. And that's the equation for it. And it comes because let's say that you have a graph over here of the force that's being applied versus time. Now, if you have an impulse, it's an intense amount of force exerted over a very short amount of time. So I can say that, let's put this in green, there's no force and suddenly there's a lot of force in a short amount of time. And our goal is to try and define the impulse by taking the integral of that curve, or trying to find the area underneath. But there's an easier way to solve this, and it's because if you figure out what the F average is, so let's assume this is the average force, and if you take the area underneath the curve of this, those two areas are supposed to be equal to each other. So it's a very good approximation, and that means I can say that F average, that I, the impulse, which is the area underneath the curve that we're trying to solve for, is equal to the F average multiplied by delta t. So I have that equation, but now I have to try and define momentum. So the first thing I have to remember is Newton's laws of motion. In Newton's second law, it says the average force, or the net force, is equal to the mass times the acceleration. So average acceleration in this case. So I can rewrite it as that. But there's also something else. I can rewrite it as I equals to m a average delta t. Still doesn't get me to what momentum is, but I can redefine the average acceleration. So let's say, but the average acceleration is equal to some change in speed over t, or delta t. So I can replace it. I have I is equal to m delta v. Exactly like this, because the t's cancel out. So what this is telling me is I is equal to m multiplied by v2 minus v1, because it's a change in velocity. So I have mv2 minus mv1. And so that term mv is called momentum. It was a quick way of defining what P is equal to. So we can define momentum is P equals to mv. And there is your equation, P equals mv. The units are going to be kilogram times meters per second, or kilogram meters per second. And so this means I can redefine impulse, not really as an intense force exerted for a short period of time. An impulse is also equal to a change in momentum. So now we really start talking about what types of forces we have to consider when we're looking at biodynamics questions and scenarios. So living systems are always in different environments, and we have to be aware of that. And because of that, it means that they're going to experience different forces. So the first step to all of these problems, especially in biophysics, is to know your surroundings. Figure out what kind of system you have first, and then you'll be able to figure out how that system is going to act on your living organism, and then you can do further analysis with that. So the next thing is, in terms of what kinds of forces are available to act on that body, your motion can be one of three things. It can occur on land. So for example, if you're walking, you can have motion in air, so if you're flying like a bird, or you can have it in water where you're swimming. So if you have an object that's moving on land, then most likely there's going to be gravitational forces and friction forces because your body is most likely going to touch the ground. You can also have elastic or tension forces in your muscle and bones that you can consider. But most importantly, it's the frictional forces. So the gravitational forces usually will act on most systems, as well as elastic or tension forces. They're quite generic, but it's the friction that changes for different scenarios. Because, for example, on land, there's static friction between my feet and the ground. But in water, there's no longer that sort of friction force. It's a different kind of friction force, which we call a viscous force, because there's going to be some sort of retarding or slowing force that's preventing you from moving. So that would be it. Of course, if you're in air, then we would have to consider drag as your retarding force, which slows things down. When we're talking about things on land, traditionally the word friction comes from the cohesive forces between two bodies that are in contact with each other. So if I have two objects that are in contact with each other and I'm trying to move something towards the right and there's friction, it means that there's a friction force acting on the other side to prevent that motion. So we say that friction will always act in the direction opposite of your intended motion. The amount of friction that you experience is going to depend on your surface roughness, your temperature, your humidity, as well as your weight. Now, for friction between two objects in contact, good to be able to label everything. Let's see. So we can draw a free body diagram of two bodies that are in contact and experiencing a frictional force. The first thing is I have the green object below and the blue object above. They're in contact, and I'll just say that over here, they're experiencing some sort of friction based on a coefficient of friction represented by mu. There are forces acting on the top box, and the top blue box is trying to move towards the right. So in this case, the object will have some sort of weight, W equals to mg. It will have some sort of normal force, which is the pushback from the bottom box onto the top box. And you will also have, your friction force. So your friction force is going to go this way because it opposes the direction of motion. So that would be a proper free body diagram for that box, if friction exists. Okay, so now I'm going to start talking about the different applications of what we've learned. So with all of the foundational knowledge done with, we can now move on to going through three different types of examples of motion. And that means motion on land, motion in air, and motion in water. So we're going to start off with motion or locomotion on land. We're going to go through walking, jumping, and propelling, and I'll introduce 2 practice problems that you can try to work on throughout the week. So when I'm analyzing motion on land, I first have to consider what forces are going to act on the system. So for inanimate objects, motion is usually caused by external forces, but for living systems, it's really important to understand that any movement is a result of internal forces because we're supplying energy to move. And that energy is going to come from different muscles. So if you're ever asked about what kind of internal forces will allow for locomotion for living systems, please do remember that the chemical energy in your body will supply kinetic energy, and then energy will be lost by friction. Work is also done during muscle action or contraction. In terms of what we're going to discuss for motion on land, we're going to study walking, we're going to study jumping, and we're going to study propelling. So these are 3 different types of scenarios that will have different free body diagrams for each. So the first thing we want to ask ourselves is, what happens when we are walking? What kind of forces act on our body? So before we even talk about walking, probably start with something simpler. Start with standing. When I'm standing on the ground is going to exert a vertical force N on your body that is going to balance your weight, or mg. This is going to allow us to stand on a surface with or without friction. So you're basically just stationary. So this isn't locomotion, this is just stationary motion, which would be considered biostatics. So if I'm standing on the ground, can I draw a free body diagram? I definitely can. I have my ground. Let's make it a little bit higher. And just bear with me. I don't want to draw my whole body. I want to draw just the leg and a foot. Okay, so there's my leg with the foot on the ground. And what this is telling me is that it's stationary, so it means I have some sort of weight, where W equals to mg. And that's going to be the force that my body exerts on the ground. But due to Newton's third law, every action has an equal and opposite reaction, so there has to be another force that's acting on your body coming from the ground. And that's going to be a normal force N. And that's pretty much it. Those are the 2 forces. There's no horizontal forces whatsoever. And so what you can say is Fy, since we're looking at the y direction only, Fy is equal to, let's consider this to be positive, N minus W. We are stationary so that the net force can balance out, so N must be equal to W, or N is equal to mg in this case. So those are the conditions for standing, and also we did a quick free body diagram for that. Next, we're going to take a look at walking, because when we're walking, the main difference is that for your foot, your heel is going to touch the ground first, then you're going to have a standing position, and then you're going to go onto your tips of your toes to provide some sort of thrust forward so that you can move. So I wanted to mention that the forward motion of any 2- or 4-legged animal can be produced by an external force. And the question is, what kind of external force allows us to move? So when we think about walking, first of all, your feet are always going to be in contact with the ground. This means that friction is absolutely essential, because if you're trying to move and there's no friction, then your feet would just slide away. So friction allows for you to have a forward thrust so that you can move forward. So in terms of how that works, we can draw free body diagrams for each step of walking. So we're going to start off with walking on the back of your feet or your heel. So this would be step 1. On your heel, I have there's my foot. Not the greatest foot, but we'll do that. And the foot is touching the ground. I know that in this case, pretending this is a point, I know there's going to be some sort of weight acting downwards. So W equals to mg. But I also know that there's going to be a normal force acting up. Now, if you think about it, if I start with my heel, what is my intended motion? Is it forward or backwards? Because now we have to take a look at where friction is. So if I'm starting to walk with my right foot, I extend my right foot out and then I put my feet on the ground. If there were no friction, my foot would most likely slide forward. So the direction of intended motion is forward, which means that friction, being a retarding force, would act in the opposite direction, which is backwards. So this means that I have friction going this way. And call this F. And so when I take a look at something called the resultant force, it would be the resultant force acting on your heel, which would be a combination of N and F together. So your resultant would be in blue. The resultant force would be something like that, which we'll call R for the resultant force. So that's the combination of external forces that are affecting your movement. Okay, so that was the first step. Now for the second step, we're in a standing position. And so a standing position is fairly easy. It means that I've already went through with my heel step, and now my feet are flat. Not super flat. As you can tell, I can't really draw feet. So there's the ground, and now for a free body diagram, we can have this dot over here. We have W, and we have N. So in this case, both of those forces are going to balance each other out, because at this particular moment when we're walking, we're actually in a vertical standing position. The third and final step is going to be when you go and thrust forward because of your toes. So this would be your toes. So you have your heel. Oops. Those are my toes. Obviously, you're going to have weight again, and then you're going to have a normal force acting from the ground on your feet. So that's going to be N. And now we have to consider, if I am now on my tippy toes, is my intended motion backwards or forwards? So if I'm doing a thrust forward, it means I'm actually pushing my feet back. So I'm trying to move back, and that means friction is going to act in the forward direction to oppose my intended motion. So that means friction is going to point here. And so therefore you would get your resultant external force in this direction. So that would be a resultant external force, and now you have the 3 different steps for walking. So in terms of what would be expected, you should understand exactly what is happening at each of these stages. So for example, as you start to walk, your big toe is going to push the ground at an angle. So I'm starting from 3. This is going to in turn apply an opposite force of reaction on your toe. And then the vertical component of that reaction force, the normal force, is going to contribute to help counter your body weight. Afterwards, your horizontal component, which is your frictional force, will give the necessary thrust to allow you to move forward with your body. So very important to understand the thrust to allow us to move forward comes from friction. And in most cases, in order to keep the foot from slipping, your coefficient of friction is usually 0.6 or 0.75 for shoes and a typical concrete floor. Now, a question is, are the vertical forces greater when you're walking or when you're standing? And think about that question for a bit, because it might be important for an upcoming conceptual quiz question. Next, we take a look at jumping. The motion of jumping is an excellent example of projectile motion. So essentially what's happening is your body is springing up and jumping at a certain angle theta with an initial velocity v. So pretty much like those Angry Birds scenarios that I was looking at before. But because you have a body, we have to consider a center of mass. So to simplify the problem, we compress our body into this point, and that is our center of mass, and we make sure we analyze all motion according to that center of mass. So when we take a look at projectile motion for living organisms, we take a look at the center of mass and how it's moving in a parabolic trajectory over a certain range. One of the equations that really comes from projectile motion, if you play around with the equations for those diagrams that we drew before, then you'll be able to come up with an equation for x, which is the range of motion, and it's going to be v squared sine 2 theta divided by g. So being able to solve for that and derive that would also be important because you should know where it comes from. Now, extensor muscles, when you're jumping, you obviously have to use your muscles. So extensor muscles are going to contract because you're usually going to be in a squatting position before you jump. And they're going to apply a force and acceleration to your body center of mass and allow it to rise a small distance s to achieve an initial velocity. So it's almost like your body's providing an internal impulse for you to start moving. So some additional equations would be v squared equals to 2as, and a is equal to f over m. So as part of a potential assignment, you might want to know how to derive these equations, just to know where they come from. So the first practice problem that I want to go through, I won't have the solutions here, but we'll present them during the live lecture. I have a man of mass 55 kilograms, and he jumps vertically into the air from a sitting position, in which his center of mass is 40 centimeters above the ground. When his feet leave the ground, his center of mass is now 90 centimeters above the ground. Due to his motion, he keeps rising until he reaches 120 centimeters at the peak of his jump. So you're asked to find two things: the average upwards force exerted by the ground on him, as well as the maximum speed attained by himself. One of the tricks here is understanding what kind of forces are actually acting on the ground and on the person. So don't forget that the man is not just standing, the man is also applying a push. So it's not just the weight of the man, it's also the weight of the man plus a pushing force on the ground. So do consider those types of forces when you're approaching this problem. I have some extra pages for you to write your solution on. The second question has to do with grasshoppers. So a grasshopper of mass 4 grams has a jumping range of 80 centimeters. So that's an actual projectile motion problem. The grasshopper leaps at an angle of 60 degrees to the horizontal, and then it moves a distance of 5 centimeters before taking the leap. So I want you to try and figure out the initial speed required to achieve this range, and also how much forward thrust is needed in order for the grasshopper to have this motion. Now, after you do that problem, you can learn a little bit about grasshoppers in real life. So in reality, a grasshopper doesn't really behave as some rigid object during its jump. It has wings, it might hover a little bit, but it also has a certain amount of force that it needs to generate in order to jump that far. So the actual value of force required is about 5 newtons of force for each of the grasshopper's legs in order for it to jump so far and so high. So this force is going to produce some sort of stress on your muscles or on the grasshopper's muscles, depending on its cross-sectional area. So depending on what grasshopper you're looking at, this one's a pretty large marsh grasshopper. And the larger your grasshopper, the larger its cross-sectional area and the more force is required to push it off. Now, in terms of analyzing this, we can start by understanding that a muscle fiber has a diameter of 100 micrometers, or micrometers, and that the cross-sectional area is 0.01 millimeters squared. Now we'll be able to figure out the stress of the grasshopper for that muscle fiber, and stress is defined as force per area. So the force, we can assume it's 5 newtons for each of the legs, and the area is 0.01 millimeters squared. So your stress is actually a lot. It's 500 newtons per millimeter squared. Now, the tensile strength you can also calculate. It's approximately 600 newtons per millimeter squared. So fairly similar. Continuing on with how we would analyze grasshoppers in real life, there's something called a safety factor, and the safety factor is the ratio of a material's strength to its expected strain. So what we analyzed before, if I go back, we took a look at the expected stress that the grasshopper would feel, but there's also the actual stress that it feels, and that's the tensile strength. So we're going to analyze, if we were to analyze the safety factor, you divide the tensile strength by the stress, and in our case, you get 600 divided by 500, which is 1.2. So it might be good to try and figure out whether a higher safety factor is good or a lower safety factor is good. Now, because we did talk a lot about mass-specific muscle power in the last lecture, it's important that we know how to apply it. So in this case, we'd actually be able to calculate the mass-specific muscle power for the grasshopper's legs. If we can assume that the leg muscle of the grasshopper is 5% of its total mass, then we'd be able to just plug in all of those values into the equation for PM and solve. So for PM, it's equal to EM over T. For EM, the only thing that we're considering at the beginning is its jump. So it's starting from the ground, no potential energy. So all of its energy is coming from kinetic energy, so 1/2 mv squared. Now the m is 0.05 of the total mass. So we replace m with 0.05 m, and you get 1/2 0.05 m v squared over t. And I'll let you try and figure out the rest because it might be based off of some of the values you calculate from your problem set. Now the next type of motion is propelling. So in terms of propelling, it's a forward motion of animals that exists for snakes and worms. So your entire body would basically be an organ of locomotion due to a lack of limbs. And if you don't have limbs, then all you're stuck being able to do is moving the parts of your body to propel yourself forwards. So usually there will be some sort of contraction of lengthy body parts and then an extension so that you can move forward. There are two types of propelling motions that you'll have to know. There's lateral undulation and there's rectilinear motion. Lateral undulation is an S-shaped movement through bending. So what's happening is you're bending the front of your body and producing a transverse wave along the rest of your length, like a snake. So essentially, what would happen is you first contract and bend the front part of your body, and it's going to send a signal to contract and to contract the rest of your body at the lateral length. With rectilinear motion, you have friction between the body and the ground, providing a forward thrust. So snakes use this too. How do they use this? The snake will first push its front to the ground. So it's basically digging its front into the ground and pulling its tails closer to the front of its body. So it's compressing the latter half of its body towards the front. After that, it's going to plant the latter half of the body onto the ground with some force and then launch the first half of its body forward. So that's the rectilinear motion. It's more linear because you're stepping forward each time. Now, the next thing I want to mention is that forces can be frictional or lateral from a reaction due to ground objects, for example, pebbles and sand. So we've talked about locomotion on land. Now we want to talk about locomotion in air. So essentially any living organism that flies will be applicable to these sorts of scenarios. We're going to go through wind force, essentially what kind of forces act on flying objects or flying animals. Then you have aerodynamics, and of course, if you have something in the air, then you can experience turbulence. So we're going to take a look at Reynolds number to let us know whether a specific animal has to compensate by streamlining its body to counteract some turbulence. So if we're analyzing motion in air, we have an eagle over here. Basically, over half of animal species can fly, which is pretty awesome. My favorite animal is birds. So birds are like living airplanes, and they employ all aspects of aerodynamics and their principles in order to fly as smoothly as they do, just like they're gliding across the air. In general aerodynamics, flying is caused by two forces. The two forces are a forward thrust, which is represented by T, from the propeller, which works against a drag force D. So that's like the friction that you have in air, a dragging force that's preventing you from moving forward. You compensate for that by having a forward thrust. Then you have a lifting force, which helps fight against your weight or gravity. So if I'm trying to fly physically, I do not have any lifting force to allow me to actually lift myself up to balance that and be able to glide in the air. Birds actually have very, very light bones, which allows them to take advantage of the wind currents, which allows them to push themselves up and counteract the weight of their body with a lifting force. So the interplay between these four forces and torques will be able to determine different aspects of motion for a flying object. So the first thing we should talk about is the wind force. What is it and how does it affect some object that's flying? So we're going to focus on a bird's wing as that object. We know that when we take a look at any living organism, it's going to have weight. So let's first draw. I'm going to draw this. That's going to be my bird's wing. And it's going to have some sort of center of mass. We'll just assume that's the center of mass over here. Now you're going to have wind acting on the system. So you have wind, it's going to be pushed up, wind going this way, and wind being pushed down. So an important part of birds is that they have a cambered profile, and that profile allows them to fly. So wind is going to blow faster above the wind than below, and then the air pressure above is less than below. What's happening here is that it causes an upwards lift force. So this causes an upwards lifting force. So we have L over here, and we know that it's going to go against your weight. So let's just draw in blue your weight. Now, as the bird is flying towards the left of the screen, it's going to experience drag, and that drag is coming from your wind. So the wind force is allowing drag to occur, and drag goes in this direction. So we have D. So there might be something else that acts on the system. And that would be your thrust, or T. So if you take a look back, you have a forward thrust from a propeller, which combats your drag force. I just want to make sure I'm not missing any diagrams or any labels here. Okay. All right, so with the drag force, I'm just going to draw a line over here so that it's on this, it's parallel to the wind force. Something I want to mention is an angle of attack. So the attack angle is basically at what angle does it hit the bird's wing. So over here, you'd have some sort of, it's supposed to be a linear line. Like that. That is your attack angle, alpha. And so with your attack angle, and this being alpha, you'd be able to do further analysis with that. Now that you have W, now that you have drag, which is trying to oppose thrust, we don't have a propeller in the system though, so we shouldn't label it with thrust. Then you have L for lift. We have something called the aerodynamic force, and that's the resultant vector of both L and D, lift and drag. So that would be something along these lines, and that would be A for your aerodynamic force. Okay. Next, I want to talk about aerodynamic efficiency. So if you have a drag force, it's going to increase with your attack angle. So what this means is, if I go back, if my wing is like this, then there's wind coming through to here, and it's not going to affect, it's not going to provide too much drag because a lot of the wind can go underneath the wing. If my wing is absolutely flat and the wind is like this, then I essentially have a perfect scenario where the majority of the wind is going to go above and below the wing. But now if my wing is like this and I'm trying to move forward, then there's a lot larger angle of attack. And that means that you're going to have a much larger drag. So that's what that means. The drag force is going to increase with an attack angle up to a certain angle called alpha m, which means the maximum attack angle. At this point, what's going to happen is it'll just decrease because it'll just pivot to being okay again. The maximum effectiveness at angle alpha m, for which L over D, wait, this sentence is weird. The maximum effectiveness at an angle of alpha m, what we're going to try and find is if your L over D ratio is at a maximum, then that is going to give you the maximum effectiveness at that specific angle. I don't think that sentence is complete. So moving forward, we have a wind force. It depends on surface area A of the wing, and then it depends on the density of air, which we represent as rho, as well as the square of the wind's velocity, so v squared. There are two terms and two equations we'll have to be familiar with, and that's basic equations for lift and drag. If you have steady flight, then your lift is going to be equal to some sort of coefficient of lift multiplied by the density of your air multiplied by the area of your wing multiplied by v squared. If you're looking at drag, you also have some sort of coefficient of drag, and that is going to be multiplied by your density as well as v squared. So these are just values that you can use to determine the lift and drag of a system that you're given. Now, if we take a look at aerodynamic efficiency, so up there, when I was talking about the attack angle, it said that there was some sort of L over D ratio. So that L over D ratio is called your aerodynamic efficiency. So you just have L over D, where LV is equal to your weight, and you have your thrust being equal to DH. What it means here is that when your wind is not horizontal, your L and D will have vertical and horizontal components, LV and DH. At equilibrium, your W and T are going to balance your L and D forces. But when they're not at equilibrium, then you'll have to separate them into their vertical and horizontal components. When we take a look at aspect ratios in flying objects, we now have to consider an object that has a really long wing or an object that has a really short wing. The thickness of the wing matters as well. So when we talk about a low aspect ratio, it means that it's getting closer and closer to becoming a square. A high aspect ratio means that it's getting closer and closer to being long, just like a rod. So here, the width, let me just put a different color. The width over here is called the chord. And then you have the length, and that's called the span. So like for birds, you have a wingspan. So the span is just basically how wide those wings can be spread apart, and then the chord is how thick those wings would be. So your aspect ratio is your best bet at characterizing what kind of a wing you have. and it's the ratio of your wingspan to your width. So AR is equal to span over chord. Now, what's important about this? Your aspect ratio is going to be proportional to your aerodynamic efficiency. So increasing your aspect ratio is more favorable to attaining greater lift to drag ratio. So now we can take a look at some bird aerodynamics. So I have another picture of the diagram that I drew for a bird's wing, as well as the different forces acting on the wing due to a wind force in green. And on the left, I also have an actual picture of, or a graphical drawing, a representation of a hawk's wing. So you can kind of see the wind is going to go over and around the wing as the bird flies. So we need to consider two things: what happens during active flight and what happens during passive flight. During active flight, birds are going to flap their wings to get the necessary aerodynamic force in order to keep gliding. During passive flight, that is when the birds will glide alongside an airstream. In terms of taking a look at differences between different species, we can take a look at the bird's geometry, their mass, and their frequency. So the frequency can vary between 10 to the 3 hertz and 1 hertz. The inner and outer wrist of the wings are going to move together to try and produce lift, just like the wind and propeller in an airplane. Let's now move on to turbulence in air. So we have streamlined airflow and turbulent airflow. Streamlined airflow is exactly like it sounds. It's good for effective, energy-efficient flights and a steady velocity. But if you have turbulent airflow, there's going to be odd and erratic variations in your flight, and that means that your velocity and your flow are going to be regularly changing. The type of airflow that you have, whether you have a streamlined airflow or turbulent, is going to be determined by something called a Reynolds number. So if any Reynolds number that you calculate for a specific object is greater than or equal to 1,000, then your airflow is considered turbulent. And in order to calculate Reynolds number, you have to be able to know the air density, rho, the velocity of the object. You have to know L, which is your span, and you also have to know eta, or the little n over there, which is the coefficient of dynamic viscosity. So some typical examples of Reynolds number for different types of living organisms. For small insects, you can probably imagine that they're very small and wind won't really affect their aerodynamics as much just because they're so small. So they don't really need streamlined flow in order to get somewhere. They're always flapping their wings. They don't really just glide. So the Reynolds number is very, very small for insects, primarily because they don't need streamlined flow. Now, if you take a look at butterflies, they have very flat wings. And because they have flat wings, it means that they already have streamlined flow. They don't have bumpy wings or anything. So their Reynolds number is going to be less than 1,000. And that makes sense. Now we take a look at a bird, like a dove. The wings are going to be arched, just like that curved bump that I drew. And it also has a cambered profile. The Reynolds number is over 1,000 for a dove, so it does experience turbulent airflow, but its cambered profile for its wings help to compensate that to achieve streamlined flow. Now, taking a look at the power of flight. The power of flight is the work that's done against a drag force per unit of time. So we say P is equal to the work done divided by T. The work done by drag, or done against drag, is going to be drag itself multiplied by a change in x divided by t. So we can consider the power of flight to be equal to dv. But before, I already had presented an equation for d, and d was equal to cd rho v squared. So we can rewrite the power of flight to be the coefficient of drag multiplied by the air density multiplied by velocity cubed. Now we take a look at a couple more terms. For a leveled flight, and leveled flight means gliding, a bird can travel some sort of maximum distance per unit time, and that maximum distance is called S-max, especially if it flies at maximum speed. So we consider S-max to be its maximum velocity, so we call it Vmax. And when it achieves maximum velocity, it will have a maximum power of flight. So we have P max over D. Next, we have weight, and it's balanced by an upward lift, where W equals to LV based on our aerodynamic efficiency. So we can express S max differently. We can now have S max is equal to P naught multiplied by LV divided by WD. So that's just manipulating those equations, and you get viscosity times P naught divided by W. So in terms of understanding how to, or understanding what kinds of questions you'll be asked to solve, my most important take-home message is to understand Reynolds number. Know how to calculate Reynolds number for a specific organism if you're given the variables and the constants for it. Understand what Reynolds number means once you solve for it, whether it's going to experience turbulent or streamlined flow, and then explain what that means for that object or for that living organism. Okay, so moving on to locomotion in water. So when we take a look at locomotion in water, we have to define a new type of friction force. There's no friction in water unless your object is touching another object. We're going to introduce viscous force as well as Stokes' law. That'll give us some new terms and new forces to play with when it comes to figuring out what sort of forces act on our living organism in an aquatic environment. Afterwards, we're just going to take a look at swimming, whether it's by fish or by humans, and then go through practice problem 2.4. Now, for viscous force, when a solid body is moving through a fluid, there is some sort of frictional force acting on the body that slows it down or tries to slow it down, and that's called the viscous force. So it's the water's version of friction. That viscous force is going to be proportional to the speed of that body in a fluid. So the faster you go, the more force you're going to feel, and that force is called viscous force. It's also obviously opposed to the direction of movement. So if you're going forward, and if you notice as you swim faster and faster, you're going to feel more of a force that's pushing against you. So that's going to be opposite the direction of movement. And all of that force, it really depends on fluid viscosity. The thicker the fluid, the more of an effect that you'll feel from that viscous force. The less viscous the fluid is, the less of a force you'll feel. So in a lot of cases, especially in physics, we try to make objects spherical. So we're now taking a look at what Stokes' law is. And Stokes' law allows us to solve for the viscous force that an object is experiencing, but we have to assume that the object is a sphere moving in fluid. So the perfect example of this would be to take a look at a spherical Pokemon, Wailmer, and try and figure out the viscous force that it experiences. So we have eta, or n, being the coefficient of fluid viscosity. You have r being the radius of the sphere, or how thick the Wailmer is. And then v is the velocity of Wailmer in the fluid, or the spherical whale. So Stokes' law basically gives you your viscous force. It's equal to 6 pi times the coefficient of fluid viscosity times r, the radius, and then multiplied by v, the velocity inside the fluid. So that is an important equation to know, because you might have to be able to solve for how much viscous force is acting on a body in water. So now that we know what kind of forces act on our objects in water, we can now analyze motion for any living organism that is in an aquatic environment. So when you're taking a look at motion in water, a lot of people try and relate it to rectilinear motion in a viscous fluid. So it's similar to movement in air, but also similar to the movement of a snake on the ground. Because most fishes, in order to swim, they're going to propel forward. Now, the weight of the body does need to be balanced for all objects in the ocean. So for small species, the weight is going to be balanced by water buoyancy. For large species, you do need an additional lift force to balance your weight, just like a shark. So the parameters are going to be the volume of your animal, the weight of your animal, the body density of the animal, as well as your water density. So there is an equation for lift force, and that's equal to V times the difference between your body and water density multiplied by gravity G. So you can simplify it and have W equals to 1 minus rho W over rho B. So back to this description between small and large species. For small species, the body density is, you have a really small body. So basically your body density is going to be really similar to your water density. So that term, rho B minus rho W, that basically goes to 0, and you get lift is equal to 0. So nothing is required. No additional lift force is required for it to float at a specific level. The only thing it needs is a forward thrust to balance its drag. And that forward thrust is produced as a fish is flapping its tail left and right. So that's where that rectilinear motion comes from. Now we can take a look at drag in water. So if we're taking a look at this dolphin over here and it's swimming, there is going to be some sort of frictional or surface drag because you have fluid going over the fish and the fish's skin has different textures. So it depends on how much surface area is exposed. So that is your surface drag, dF. The next type of drag that you have is called a pressure drag. And that pressure drag is due to the longitudinal stress on a fish by the flowing stream of water. So it depends on the shape or the transverse cross-section of the fish's face. So the pointier the nose of a dolphin or the pointier the nose of a fish, the less of a pressure drag it's going to feel. The wider the cross-sectional area, the more of an effect it will feel. So it's important to note that when you take a look at your surface and pressure drag, they really just depend on the size and the velocity of the fish or the object that you're looking at. One of the things to mention is that fish actually cannot move at high speeds, but what they can do is accelerate quickly because their tails are very strong and they can thrust forward very quickly as well, at around 40 meters per second squared. So now wrapping up the 3 types of locomotion that we talked about on land and water and also in air. Gravity was present in all of them, so we have to consider the role of gravity in each. One of the things that's important to understand is gravity is not uniform for all these different situations. Although we know that the average is 9.81 meters per second squared, it can actually range from 9.77 to 9.83 meters per second squared. Animals can adjust to gravity by changing their skeletal and cardiac properties, and plants are affected through directed growth. So sometimes they grow towards the sunlight, which defies gravity. In the body, your particles are going to move down because of gravity, according to Stokes' law. So the parameters are going to be fluid flow or fluid viscosity, particle density, and medium density, and medium being the surrounding that you're in. So in order to apply that, you equate Stokes' law to an equation we had before, which was a change in density multiplied by g for the lift. Now for small particles, gravity is going to be balanced by thermal motion. So by thermal motion, we have 1/2 mv squared is equal to 3/2 kT, where k is Boltzmann's constant and temperature. So this we won't focus on as much, but it is important to know that gravity isn't always uniform everywhere. So practice problem number 2.4 goes through being able to calculate the amount of power that's spent by a propelling bacterium. So we're trying to figure out how much power is required to have that bacterium coast at a speed of 20 micrometers per second against some viscous drag force. Okay, so that pretty much sums it up for this lecture. I'm going to go through a summary of what you should remember now. So essentially what we've talked about in this lecture is a bunch of different ways that living organisms can move in different media. So you can move on land, you can move in air, and you can move in water. So very important to understand what forces are going to act in various cases of biodynamics. So in each of those scenarios, you'll have to be familiar with the following physics foundations. So kinematics and projectile motion, Newton's laws of motion, as well as forces. You'll have to know in some detail the different types of locomotion that we covered. So walking, jumping, and propelling. Do know some of the biology and do know some of the methods of those motions as well. Do know about flight and aerodynamics, as well as viscous force and swimming. So in flight and also in swimming, there were different types of lift and different types of drag. Know the differences between each one and what the variables mean, or the parameters. And of course, understand different types of friction forces. In every single scenario, there's always something that is going to oppose the intended direction of motion. So anything that opposes the intended direction of motion and comes from the environment is usually a type of friction force.